We're finishing off our first section. Well, not quite. There's a little bit more to do, but here's some more stuff about correlation. So remember correlation, we computed the correlation for that data, we got 0.961. Here's some facts about those correlation coefficients. This correlation is a description of the strength and direction of a linear relationship without outliers. Positive R indicates a positive association. So positive just means when X increases, Y increases. So if you think of a linear pattern, so we're thinking of a linear relationship when we talk about correlation, then that linear relationship should have a positive slope. Negative R indicates a negative association. That means the pattern has, the line representing the pattern would have a negative slope. Correlation is always between -1 and 1. We'll see later that scoring the correlation coefficient gives you a number which can be interpreted as the percent of the variation in Y that's explained by a line that goes the direction of the data. But right now we'll just say correlation is always between -1 and 1. Values near 0 indicate very weak linear relationships. If it looks linear already and you get an R near 0, then it's that means the relationship, there's no real strong pattern. The linear pattern you're seeing isn't very pronounced. But you can also get values near 0 for a strong curved relationship where you can easily predict Y from X, but the relationship is curved. And so R is only good for predicting the strength of linear relationships. Values near 1 or -1 usually indicate a very strong linear pattern, but can also happen because of a single outlier. So the value of the correlation coefficient can be impacted by one extra value which is improperly entered. In fact, you could have a pattern that is strong and negative and linear, and when you add one extra point all the way to the right and near the top of the graph, so that point seems to have a positive association with the rest of the points, then R will come out to be a positive number, even though in most of the data, with the excepting the outlier, the pattern has a negative association. So you have to be careful before you compute R and talk about R telling you how strong the relationship is. You might want to look at the graph to make sure you're looking at something that's linear. And if you're comparing linear patterns, then you can compare R values. But if you're not comparing linear patterns, then it doesn't make sense to use R values. More stuff about correlation. Correlation makes no distinction between explanatory and response variables. They appear in a similar formula or symmetric manner in the formula. If you swap X's and Y's, nothing happens to R. So if you don't know which one's explanatory and response, you don't have to worry. When you compute R, you get the same number either way. Second statement is, since the values used to compute R are standardized because they're z-scores, they're unit independent, so you get the same z-score no matter what units you use to describe the variables. And so no matter what units you use to describe the variables, you get the same value for R. So if you measured in degrees Fahrenheit, degrees centigrade, measured in feet or yards or miles, it doesn't matter. You get the same kind of R value as you compare the two variables. Third statement, R is only useful for measuring the strength of a linear relationship. We knew that. R squared is a better choice than R if you want to gauge the strength. And we'll see why R squared matches your intuition better than R does. So, you know, R close to 0 means not much of a pattern, but actually R has to be pretty far away from 0 for a pattern to really be reasonable. So maybe R has to be bigger than 1/2 or less than -1/2 before you start to see the pattern that might be useful. So any R's between -1/2 and +1/2, if you look at the pattern, you don't really see much pattern, so there's not much use to the pattern. You'll see that later on. And then cautions. Do not use correlation with curved relationships. It does not indicate the strength of a nonlinear pattern. Correlation, like mean and standard deviation, is strongly influenced by outliers. We say it's not resistant to outliers. We like having resistant measures of things because ordinarily we might not notice there was an outlier, and then if the value dramatically changed because of one outlier, then we don't have a way of thinking about the data set in general terms because the single outlier changes the value of that particular computed value. So we hope we could use things that are resistant to outliers, but we can't always do that. Something like the median is resistant, but something like the correlation isn't resistant. So you have to graph the data first before you compute correlation and use it. Correlation is only a description of the strength and direction of a linear relationship. We will soon be able to find the equation of the line representing the data. So correlation is a description of strength and direction of a linear relationship. If it's linear, maybe we should find the line that you would use that best fits the data, and that'll be called the regression line or the least squares line, and we'll be doing that shortly in this section. But right now we don't have it yet. So right now we can use that for just strength and direction, but we'll have a more complete description of linear relationships later when we get the equation of the best fitting line. And that ends this particular set of this particular video for this first section of chapter 4. We've got one more to go, and then 4.1 will be behind us.